So here we're going to attempt to integrate this ugly looking rational function. So there's nothing really you can do with U substitution here if you check it out. It is a proper fraction, so I'm going to try to factor the bottom and maybe use partial fraction decomposition. So the bottom is not the easiest factoring problem, but the one thing, if you remember all the P over Q stuff, the only possible rational zeros of this would be plus or minus 1. So you can check that out with synthetic division, or you can just look at it now. If you plug in 1, you'll get 1 minus 3, negative 4. 1 minus 3, negative 2. Plus 3 is 1, minus 1 is 0. So you know positive 1 is a 0, or x minus 1 is a factor. So to get the other factors, I'm going to actually run it through the division. So I know 1 is going to work. 1, negative 3, 3, negative 1. This will help me find the other factors that go along with it. So bring down the 1, multiply 1 times 1 is 1, add, you get negative 3. Multiply 1 times the negative 2, add, you get 1. Multiply 1 times 1, which is 1, add, you get 0. That just confirmed that 1 is a 0 and x minus 1 is a factor. So the leftover quadratic looks like this. This factors into x plus 1 times x plus 1, or x plus 1, x minus 1 times x minus 1, or x minus 1 squared. Our original 0 was 1, so that brought about a factor of x minus 1. So this denominator factors like this. X minus 1 times x minus 1 times x minus 1. So if you try to break this down into the normal linear partial fractions, it wouldn't work, because if you have these are all the factors, there's nothing that differentiates these factors. So whatever you try to do here, you're always going to get an equation that will get you like 0 equals 0. You'll never be able to get the A, B, or C to drop out. So the method to do this, it's called repeated linear factors of the bottom. You would do it like this. A over x minus 1 would be the first partial fraction, and then plus, instead of going b over x minus 1 as well, square that factor. So if it was just x minus 1 quantity squared, I'd be done. But now you keep going until you get to this 3. So if it was to the 4th, you'd use more. But at this point, I'm there. Now what that does is it differentiates all of these little fractions, so that when you go to solve this, you'll get different equations. A, B, and C will be distinguishable, and you'll be able to solve for each one of them. And this is still the common denominator as the original problem. So hopefully that made sense. So now I'm going to just go about as usual. I'm going to multiply everything by the common denominator, x minus 1 cubed. So we have if you multiply the first one by x minus 1 cubed, you'll have x minus 1 squared left over. For the b term, you'll have an x minus 1 left over. And for the c, you'll just have the c, because that whole thing canceled out. So now we're ready to start solving. It's going to be very simple to solve for c. We'll just let x equal 1. And then we will have 1 plus 2 minus 2, which is 1. A and b are nothing, so we have c equals 1. Now we have to solve for a and b, and the problem here is there's nothing we can do to have c drop out. So we're going to look for like really simple numbers to use. I'm going to use x equals 0, and that would give me negative 2 equals a times a negative 1 squared, or just a, plus b times a negative 1, and then plus c. C we already know is 1. So this would get you a minus b equals a negative 3. So now we have to choose another number to get another equation with a and b, and then we can use any method we know to solve a two equation system to solve for a and b. You'll see. So I'm going to pick another number that's going to work well, and I think I'll try negative 1. When you plug negative 1 in here, you're going to get positive 1 minus 2, which is negative 1, minus 3, which is negative 3. I'm just going to double check that. 1 minus 2, negative 1 minus 2 is negative 3. Yes. When you plug this into the a term, you get negative 1 minus 1, which is negative 2 squared, which is 4. So 4a. Plug it into the b, you'll get negative 2 times b, negative 2 times b, so negative 2b. And c is still 1, so that gets you this equation. 4a minus 2b equals negative 4. So now I have this two equation system with two unknowns. I like to do it by eliminating one of the variables, a or b. To do that, I guess I will just multiply the top equation by a negative 2, because that would get the b's to be completely opposite, and that would get the b's to drop out immediately. So this would be negative 2a plus 2b equals 6. This equation I'm going to do nothing to because I don't have to. 4a minus 2b equals negative 4. And now I can simply add these together. I have 2a equals 2. That's nice. A equals 1. So now I can solve for b just by using either one of these equations. I'll use this one. So I have 1 minus b equals a negative 3. So that would be b equals a negative 4. Negative b equals negative 4, or b equals 4. So I have a equals 1, I have c equals 1, I have b equals 4. So now I'm going to write my partial fraction decomposition, which would be a over x minus 1 plus b over x minus 1 squared plus c over x minus 1 cubed. So that should be equivalent to the original one, assuming I did everything right. So now we're just going to integrate that. Hopefully this works out well. We'll see. Well, the first, you're going to break this up into separate integrals. First one's going to be a natural log. The other two are going to be easy because if you think about the u substitution, you're going to have u equals x minus 1. So du equals dx. So there's no constant. So you're just going to do the first one or the second one like for u to the negative second, and this one like u to the negative third. So I'm going to do that mostly mentally. The first one is an obvious natural log. The second one, we're going to integrate for u to the negative second. So that would be u to the negative first times a negative 1, so minus 4. And then the third one, when we integrate, you'll get u to the negative second times a negative 1/2. So this would be minus 1/2. Clean it up just a little bit here. We have natural log of the absolute value of x minus 1 minus 4 over x plus 1 minus 1 over 2 times x minus 1 squared. And since I'm on a roll here, let's get a common denominator on the rational functions. We'd have to multiply this one by 2 times x minus 1. I saw that. I changed that to a minus. So we'll multiply this one by 2 times x minus 1. So it would be 6 times x minus 1. 8 times x minus 1 up top, or 8x minus 8. So that was just getting a common denominator. So now I can add up the tops. Apply this negative to the top, so it's plus a negative 8x plus x. I have minus 1 from the second fraction all over that common denominator of 2x minus 1 squared. I have natural log of x minus 1 plus negative 8x plus 7 all over 2 times the quantity x minus 1 squared. That's all I'm going to do. Add a plus c there, and that is that. So did a little preview on Wolfram Alpha. There's the answer. 1/2 negative 8x plus 7. That looks good. So there you go. That is it. I'm going to stop right now.